Today I'm going to talk about the quantum theory of measurement. Measurement is an important type of quantum computation. It's also, of course, what links quantum theory with experiment. But for historical reasons, unfortunately, the quantum theory of measurement also plays a prominent role in what we could call quantum mechanics folklore, the informal misunderstandings of quantum physics that range from careless remarks in textbooks through bad philosophy and all the way down to complete nonsense. You may have heard that the measurement process in quantum theory is deeply mysterious and spooky, that it has a special role for the conscious observer. You may have heard that when you make a measurement in one place, there's an instantaneous effect on quantum systems in a different place. And you may have heard that measurements are inherently irreversible processes, even though the laws of motion in fundamental physics are all reversible. As you'll see in this lecture and later lectures, none of that is true. In fact, quantum measurement theory is pretty well understood and has been a powerful tool for understanding quantum physics. Nowadays, it's part of the quantum theory of computation. The most elementary but important thing to understand about measurements is that they are physical processes that we understand using the same theory and laws of physics as we do for all other physical processes. A measurement is a process in which one physical system, a measuring instrument, interacts with another physical system that's being measured, and some observable of the measuring instrument is affected by some observable of the system being measured and ends up, ideally, having the same value. Let's confine our attention for the moment to the useful idealization of a perfect measurement. We can define a perfect measurement process by the effect it has when the observable being measured is sharp, has a single value. First, the outcome of a perfect measurement of a sharp observable is the value of that observable. And second, at the end of the measurement, the observable being measured is still sharp with the same value it had before. So, a perfect measurement records sharp values accurately and leaves them unchanged. The simplest possible measurement is the measurement of a Boolean observable, where the outcome is stored in a second Boolean observable. Let's think about that first in the case of a classical computation. Let's make it a reversible classical computation, partly to substantiate what I said just now about measurement not being inherently irreversible, but mainly because, in fact, classical reversible computations are a special case of quantum computation. Imagine that we have a single bit that we're going to measure, and the bit has an unknown value that's either +1 or -1. Call that unknown value A. And we have a second bit somewhere in an apparatus in which we want to record a copy of the value of the first bit. The second bit is called the target bit. So the target bit has to end up with the value A. And the bit being measured has to keep the value A. Considered as a computation, perfect measurement is a process of faithfully copying information, so that where there was one copy of the sharp value of the observable, there are now two, the second one being in the measuring apparatus. As far as the definition of a perfect measurement is concerned, we're not interested in what the initial value of the target bit was, so long as the final value is A. But in a reversible computation, different inputs must always produce different outputs. So it follows that if the computation only involves those two bits, it can only be a perfect measurement for one initial value of the target bit, let's say for the value +1. So it's not a perfect measurement when the target bit starts at -1. What does happen if it's -1 depends on the law of motion. And one interesting law of motion is that of a very useful operation called controlled knot. The ordinary knot operation is the single bit or single qubit operation that figured in the interference experiment I discussed last time. It flips +1 to -1 and vice versa. Controlled knot means flip the value of the target bit only if the first bit is -1. The first bit is now called the control bit. If the control bit is +1, the target bit remains unaffected. So we can summarize this controlled knot operation like this. If the input values of the control and target bits are A and B, then the outputs are A and AB. A computer like this that performs a simple computation on a fixed number of bits and completes it in a fixed time is called a computational gate, also known as a logic gate. And in this case, it's a reversible logic gate because it's performing a reversible computation, the controlled knot operation. Let me just summarize some of the ways in which we can think about what the controlled knot gate does. First of all, if B equals +1, then considering it as a physical process, it's a perfect measurement. The first bit starts with an unknown value, A, and the second bit ends up holding the measured value of the first bit, which should also be A. Second, considered as a computation, if B equals +1, then the process copies information. The information A, which starts out in only one of the bits, ends up in both of them. Third, for an arbitrary B, well, that's the controlled knot operation. The target bit is flipped if and only if the control bit is -1. And a fourth interpretation, this gate is the reversible version of the classical exclusive OR gate. If we consider +1 as standing for false and -1 for true, then A times B is the same thing as the exclusive OR of A and B, and the target bit ends up as the exclusive OR of the two inputs. And as I said, like all classical reversible gates, the controlled NOT gate has a quantum implementation that works on 2 qubits instead of 2 bits. That's the quantum controlled NOT gate. In some implementations, there's a physical object you can identify as the gate, as with the mirror in the interference experiment last time, which was a NOT gate, and the beam splitter, which was a fractional power of NOT. But speaking more precisely, the computational gate is not the object that makes the process happen, but the dynamical process itself that's undergone by the qubit or qubits that physically realizes a rule that defines each output in terms of the inputs and nothing else. Now, to describe the quantum physical system consisting of 2 qubits passing through a quantum controlled NOT gate, we're going to make the Z observable of the control qubit control the Z observable of the target qubit, to describe that quantum system, I have to tell you, as always, the static constitution, the dynamics, and on each particular occasion when the experiment is done, the state, which summarizes how the qubits were prepared as the input. I'll start, as usual, with the static constitution. For this, I have to tell you the algebra of all the observables at any one time, which will then be the same as the algebra at any other time, because the algebra summarizes the time-invariant features of a quantum system. So, here we have a 2-qubit quantum system. We already know what the algebra of the observables of either one of the 2 qubits is, because that algebra is itself an invariant. It's the same for all qubits, and regardless of what interactions the qubit happens to be undergoing. So, as in the 1-qubit interference experiment, the first qubit will have observables x, y, and z, which have the same algebra as the Pauli matrices, together with the unit observable, and linear combinations of those with constant coefficients. Let me call these observables x1, y1, and z1 now, where the suffixes indicate that they are observables of qubit number 1, the control qubit of the quantum-controlled NOT gate. We don't have to put a suffix on the unit observable because, as you'll remember, the unit observable can be measured without even referring to the system it's an observable of. The second qubit, the target qubit, will have different observables, x2, y2, z2, and so on, but they'll also have the Pauli algebra. Now I have to specify all the additional algebraic relations that may hold involving observables from both qubits. And here's a universal rule that defines the algebra of any composite quantum system given the algebras of its constituent systems. It just says that the observables of different quantum systems commute with each other. That is to say, if A1 is an observable of one system and B2 is an observable of another, then A1 B2 equals B2 A1. I told you last time that 2 by 2 matrix representations of a qubit algebra wouldn't always be enough. Here's why. This set of algebraic relations can't be faithfully represented by 2 by 2 matrices. This set by itself can, so can this set. But because this commutation relation for the combined system has to be represented as well, qubits 1 and 2 can't use the same set of matrices. Take Z2, for instance. It has to commute with every observable of qubit 1. But the only 2 by 2 matrices that commute with every 2 by 2 matrix are multiples of the unit matrix. And Z2 can't be represented by a multiple of the unit matrix because it's a Boolean observable. It has to have 2 distinct eigenvalues, and the multiples of the unit matrix have only 1 eigenvalue. So there is no 2 by 2 matrix representation of this algebra as a whole. The simplest representation turns out to be a 4 by 4 representation. And the way it is constructed applies to any 2 quantum systems, not just a pair of qubits that you want to consider as a single system. It uses the tensor product of matrices. The tensor product of 2 matrices of dimensions m and n is an mn dimensional matrix consisting of all possible products of pairs of elements, one from the first matrix and one from the second, like this. A, B, C, D with E, F, G, H is the 4 by 4 matrix, AE, AF, and so on. That symbol denotes the tensor product. So the tensor product of a pair of 2 by 2 matrices is a matrix of all 16 possible products consisting of an element of the first matrix multiplied by an element of the second. You can verify in the worked examples that the tensor product of two Hermitian matrices is a Hermitian matrix. So the tensor product of two observables, one from each system, is an observable of the combined system. What observable is it? Well, if you have two systems and A is a matrix representing an observable of system 1 by itself, and B is a matrix representing an observable of system 2 by itself, then the tensor product A cross B is an observable that you measure by measuring A on the first system and B on the second, and then multiplying the results together. You can verify that the tensor product operation is associative, but it's not commutative. In other words, A cross B is not the same as B cross A. You can also verify that the tensor product has the following property with regard to ordinary matrix multiplication. A cross B times C cross D equals AC cross BD. Now, it follows from all that using the tensor product, we can make a 4 by 4 representation of the algebra of observables of qubit 1 as follows. Just multiply each matrix of any 2 by 2 representation by the 2 by 2 unit matrix on the right. These are now 4 by 4 matrices. And because of this property, it's easy to show that they do indeed represent the standard algebra for one qubit. For qubit 2, we can do a similar thing, this time multiplying by the unit matrix on the left. They too form a 4 by 4 representation of the standard algebra for a single qubit. And the object of the exercise, any observable of the first qubit commutes with any observable of the second. For instance, x1, y2 at time 0 is sigma x cross 1 times 1 cross sigma y, which equals sigma x cross sigma y. And taking it the other way around, y2x1 equals 1 cross sigma y times sigma x cross 1, which also equals sigma x cross sigma y. By the way, like in the single qubit 2 by 2 case, we need never work with the actual components of these matrices. Every 4 by 4 Hermitian matrix can be expressed as a linear combination of tensor products of the form sigma cross sigma, and sigma cross 1 and 1 cross sigma, and 1 cross 1, which is the 4 by 4 unit matrix. So again, we can just express all 4 by 4 matrices, and so all observables, in terms of Pauli matrices, and do all matrix arithmetic in terms of the algebra of Pauli matrices. So, I've told you the static constitution of a pair of qubits, which would be the same for any 2-qubit gate. Now, the dynamics of the controlled NOT gate in particular. As usual, we'll imagine that it performs its operation in one unit of time, one computational step. For the moment, we're considering the gate as an elementary quantum computation, so we're not interested in its internal workings. We're only interested in how the output depends on the input. So for present purposes, the dynamics of the gate just means how the observables at time 1, after the gate has acted, depend on the observables at time 0. Well, the dynamics of a controlled NOT gate are defined by a set of equations, most of whose details are not relevant for present purposes, but I'll put them on screen anyway, just so that I can point out the highlights that are relevant. These 6 equations tell us how 6 representative observables change, 3 of them from one qubit and 3 from the other. We don't have to list the unit observable explicitly because it never changes. Using these equations, we can find out how any other observable behaves as well by expressing it at time 0 in terms of these representative observables, and then using the fact that algebraic relations between observables at a given time don't change with time. These equations are actually redundant. We could make do with just 4 of them because, for instance, the static constitution for any qubit already defines its observable z at any given time in terms of its observables x and y at that time. Now, take a look at the equations for the time evolution of just the z observables. You can see that z1 and z2 at time 1 depend only on z1 and z2 at time 0. The x's and y's don't affect the evolution of the z's. So the z observables almost form a physical system in their own right, a little subsystem of the 2-qubit system that evolves independently of the rest. It doesn't quite count as a separate physical system because you can never change z without changing x or y. Nevertheless, in a controlled NOT computation, the z observables are autonomous. They're evolving independently of all other observables. I've drawn your attention to that because it will come up again in later lectures, but for the moment, its only significance is that it makes it easy for us to check that this gate really does perform a perfect measurement. Remember, a perfect measurement interaction is defined by what it does when the observable being measured is sharp. So now it's time for me to specify a convenient state for our 2 qubits in which the z observables of both qubits are sharp. There are only 4 possible cases of this, so we may as well deal with all 4 of them wholesale. Let the observable z1 be sharp with the value a, and let z2 be sharp with the value b. A and b are each plus or minus 1. So to specify the state, or actually 4 possible states, we have to specify the expectation values of all the observables. And I've just said that the expectation value of z1 of 0 equals a, and the expectation value of z2 of 0 equals b. As I mentioned in the last lecture, and you will have proved in the worked examples, z being maximally sharp implies that x and y are both minimally sharp. In other words, that their expectation values are both 0. This in turn tells us how to find expectation values of Pauli matrices in this state, in the representation we've chosen for the observables. We have expectation value of sigma z cross 1 equals a, and expectation value of 1 cross sigma z equals b. By linearity, this tells us all the expectation values of matrices of the form something cross 1 and 1 cross something. You'll see in the worked examples that these relations also tell us that in this state, the expectation values of any tensor product of the form A cross B where A and B are 2 by 2 matrices, is the product of the expectation values. With these rules, we can find expectation values of general matrices and hence of general observables in this state. So, what do we predict for the output of the controlled NOT gate where the inputs were sharp? Well, the control observable Z1 has the same expectation value at time 1 as it did at time 0, namely A. And since A is plus or minus 1, that means that Z1 is still sharp with the value A, which is correct. Z2 is sharp as well, but its value has changed. It's now AB, just like the target bit of a classical controlled NOT gate. Okay, the next obvious thing to work out is what happens if we perform a perfect measurement of an observable that's not sharp? Well, you can prove in the worked examples that if Z1 isn't sharp at time 0, it'll be just as unsharp at time 1. And also, Z2 will have become just as unsharp as well. So, the measurement interaction propagates unsharpness from one system to the other. But there's more. Consider the observable Z1, Z2. That is an observable because Z1 and Z2 commute at any one time, so Z1, Z2 is Hermitian. And from what I've said, its operational meaning is that it's the observable for what you'd get if you measured Z1 and Z2 and multiplied the outcomes together. In other words, it's a Boolean observable whose eigenvalue -1 means that the outcomes of measuring Z1 and Z2 would be different, and +1 means that those outcomes would be the same. Now, here's a remarkable thing. Starting in a state where Z1 is not sharp at time 0, and hence both Z1 and Z2 are unsharp at time 1, calculate the expectation value of Z1, Z2. You'll find it's +1, which means that the observable Z1, Z2 is sharp. In other words, Z1 and Z2 are equal at the end of the measurement, sharply equal, even though neither of them has a sharp value. How can two things be perfectly equal without either of them being sharp? Well, like this, of course. Finally, let's look at the case where this measurement of an unsharp observable takes place in the middle of an attempted interference experiment. Let's work out what happens when we combine the analysis of the previous lecture of the interference experiment with this time's analysis of the dynamics of measurement. Let's take a qubit based on the photon's direction of motion and pass it through a beam splitter to make Z1 of 1 non-sharp. So, from the equations of motion, Z1 of 1 takes this form in the 2 by 2 representation of last time. But now we're going to measure the direction of motion. So we need a second qubit and therefore a 4 by 4 representation, like this. The second qubit will be a subsystem of some instrument that detects the direction of motion. In principle, that could be another subatomic particle, but equally, it could be a pair of photon detectors like the ones we actually used in the interference experiment. The essence of any such instrument is that somewhere in there is an observable that's going to be the target of a controlled NOT or perfect measurement operation. a Boolean observable, measuring the z observable as we defined it for the photon's direction of motion. So, we can just analyze those two qubits and forget all the other degrees of freedom, just as we did before. The details, again, are in the worked examples. We find that the expectation value of Z1, the photon direction of motion, at time 2, just after the measurement, is 0, just as it was in the original experiment, because in half the universes the photon travels on one path, and in the other half it travels on the other. And so the expectation value of Z2 of 2 is also 0, just as we would expect from something that has measured the correct value of Z1 in each universe. Then we let the photon go on and do exactly what it did before, namely bounce off the mirrors and strike the second beam splitter, which previously had the effect of making the direction of motion sharp again. But look, not in this experiment. The expectation value of Z1 is still 0 at the end of the experiment. The fact of having made a measurement, even a perfect measurement, of the value of Z1 at an intermediate stage of the experiment has spoiled the interference phenomenon. This is why we don't see very clear examples of quantum interference in everyday life. It's because undergoing an interaction in which even one qubit from the outside is affected by a physical system is enough to suppress interference. And it doesn't have to be a measurement interaction. You'll see that almost any interaction affecting an outside qubit will do. Specifically, what prevents interference is when something carries off information about the system. And the reason why that makes a difference is that any process that transfers information out of a system always changes the system itself. If the process is a perfect measurement, it doesn't change the observable being measured, say Z, but it changes other observables like X or Y that are inextricably linked with it by the uncertainty principle and by the dynamics of quantum physics. And that can make the system subsequently behave differently. A process in which information is carried off in this way is known as a decoherence process. In practical implementations, decoherence is the great enemy of quantum computation, and I'll be saying more about that. So far, when I've described the dynamics of quantum systems to you, they've all been quantum gates, I've always just told you the laws of motion of the gate by fiat, just a set of equations for how the representative observables of the qubits are changed by passage through the gate. In the next lecture, I'll show you a general framework for quantum dynamics, and I'll tell you in principle which sets of such equations describe processes that can occur in nature and which can't.